Hi everybody. So we're going to finish up the chapter 5 notes in part 3 here. We're going to kind of pick up where we left off. We had introduced this equation that talks about how to calculate heat of reaction based on tabulated heat of formation data. So we're going to use this equation to calculate the heat of formation for the reaction we were looking at earlier, the combustion of propane. So C3H8 and oxygen goes to carbon dioxide and water. So I'm going to use this idea that I can look up the heat of formation of everything in that equation, and if I do that for the products and subtract the reactants, I'll get the heat of reaction. So I start by filling in what my products are, CO2 and water. My coefficients are there. You notice that the 3 is from the equation. That's where I got this 3 from, because there's a 3 with the CO2 up here. All right, and the same thing with the water. There's a 4 and a 4. And then I'm going to look up the heat of formation for everything that's in that reaction. So I have to be careful about the states. The 393.5 is for carbon dioxide gas. The 285.8 is for liquid water. So I got to match the states. And then I subtracted my reactants. And you notice that the heat of formation of oxygen is 0. All right, that's because the heat of formation reaction is for producing something from its elements as they exist at room temperature and pressure. And that's how oxygen exists at room temperature and pressure. And so there's no change, essentially. So one way to tell what the normal state of something is if you're looking in Appendix C to find a heat of formation and it has a heat of formation of 0, then that means that's how it always occurs. So just added all my numbers together, and then I came up with a negative 2219.9 kilojoules for that reaction. So you can do this for any reaction as long as you can look up the heats of formation. So here's another problem with the iron oxide, and oxygen goes to Fe2O3, and you should cover up the answers to this and try this problem again. Make sure that you get the same answer that I did. Another way that we can use Hess's law is to put together different types of reactions and to add the reactions up to get the overall reaction we want. Now this is something we did in the Alum lab. We looked at adding reactions together. What's a little different here is I have to kind of figure out how to arrange the reactions. So they've given me 2 reactions in this problem. So the first reaction, they're telling me that if I take solid carbon and oxygen and make carbon dioxide gas, that my heat is 393.5 kilojoules. And in the second reaction, I've taken carbon monoxide and half of an oxygen and made CO2 gas. And they gave me a delta H for both of these. And what they want me to do is to figure out how to rearrange those equations so that I can come up with a heat for this bottom reaction. So my goal, essentially, is to come up with a heat of reaction for this bottom reaction. So what I have to do is I have to look at the 2 equations that I'm given and figure out what to do with them. So I'm probably going to have to switch their order around a little bit, or multiply them or divide them. And remember that whatever you do to the reaction, you do to the delta H. So this is what this looks like. So in order to use those 2 equations, all right, I have to make sure that I have the carbon on the reactant side. So I just rearrange the equation so that my carbon is on the reactant side, and my oxygen goes to CO2. And then in the second reaction, I essentially have switched this around so that my CO2s cancel out, and my CO, which is a product, ends up on the product side. So what I did with this second reaction is I changed its order. So because I changed its order, I changed the sign on the delta H. So I reversed this equation. And now when I add these together, the CO2s cancel out, and I'm just left essentially with what I want. So half of an oxygen on one side and an oxygen on the left. That half cancels out, and I'm left with a half over here. So I end up with a half of an oxygen on this side once I cancel that one out. So we end up with the reaction that I want. Okay? So it's just another method for calculating the enthalpy of the reaction. So the last few slides in here talk about the relationship between calculating heats of reactions and how that affects what we would refer to as foods and fuels, how we calculate those for foods and fuels. So foods are metabolized in our bodies through a very complicated sequence of reactions. But the end result is essentially the same as a combustion reaction because I'm essentially breathing in oxygen and breathing out carbon dioxide. Most starches in our bodies are converted over to glucose, and so then the glucose is combusted in our body. So see if you can write a reaction for the combustion of glucose, C6H12O6. So there's the reaction. And the delta H for this reaction is negative 2803 kilojoules per mole. And this could be measured the same way like through bomb calorimetry, or I could calculate this by looking up the heats of formation of everything in the reaction, and I would come up with 2803 kilojoules per mole of glucose formed. Fats are metabolized very differently, okay? So fats can be approximated as C57H110O6. Combustion reaction still, my fuel, which in this case is the fats, plus oxygen goes to carbon dioxide and water. So this has a very different value of delta H. It's 75,520 kilojoules for that reaction, or what works out to be 38 kilojoules per gram. So see if you can calculate how many calories are in 5 grams of fat. How would I make that conversion? It's just a conversion. So 5 grams of fat, the value I've been given is 38 kilojoules per gram, and then I can change kilojoules to kilocalories by using conversion we had way back at the beginning of the notes. And it works out to be 45 kilocalories, or 45, I should say calories, I'm sorry. So the big C calories, those are nutritional calories. All right, so that is the end of the notes for Chapter 5. There's a practice sheet up. There are questions on mastering chemistry that you can practice on. And then, as I mentioned earlier on Blackboard, there's a quiz on mastering chemistry, and there will also be a quiz that will open up on Blackboard on this chapter. You can, I haven't posted my office hours yet, but I'll be doing that really soon. Probably by the time you're looking at this, they'll be up. So you can also contact me at my office hours and ask me questions about how I did some of these problems if you're having trouble. Read your book. It's your best friend now. So read your book and work on the sample problems that are in the book.